do from your homework is something that was asked by a student in third period. They asked about this question. They said it had a spring in it, that there is a spring that's unstretched length was 10 centimeters, and that when they added a 2 kilogram mass, it stretched to 15 centimeters. They wanted to know what the spring constant was, and they wanted to know how far would it stretch if you put a 3 kilogram mass on it. Now, I don't think this is a particularly hard question, but I have a follow-up that I think is hard. So this is why I want to talk about this question. Do you guys recall this question from the homework? All right. So the state of the problem when it is at rest here, would you agree there's only two forces acting on it? There's the weight acting downwards, mg, which for this one would be 20 newtons. Although if this problem is out of the book and you're trying to compare your answer to the back of the book, you might have to use 9.8, but I'm just going to use 20. And then the upward force, what do you want to call that? Tension? I mean, it doesn't really matter. I hope you're getting to a point now where we just have these names to help us think about types of forces that act. Tension is going to have a lot of different meanings throughout the course of the year, but this is actually the force from the spring. Now, we talked about the force from a spring. It obeys something called Hooke's law. And although I didn't really go into it at all, Hooke's law is merely the force a spring will provide when stretched or compressed. It applies to anything that has an elastic nature to it. And I know we just talked about it yesterday or the day before, and we didn't really do anything with this, but there's not a whole lot to do with this. But practice is important. So do you notice that there's a negative sign in here? I want to be really clear about this negative sign. The negative sign is to tell us that if you pull out on the spring, it will pull back. And if you push in on the spring, it will push out. Or in this case, if I pull down on the spring, it will pull up. It's just about direction. I'm saying that because net force equals 0. I'm going to say the force from the spring minus the weight equals 0. I'm making the force from the spring upwards because that's the direction it acts. The negative sign is just to remind me that the spring pulls in the opposite direction from its displacement. It's a restoring force. You guys are smart. If I put a plus here, do you recognize what the difference is? One of these is a restoring force, one of these is not. With the negative sign, it's considered a restoring force. Without it, it's a destructive force. If you don't understand, both of these systems can have equilibrium. If I make x 0, the force is 0, that's equilibrium. Consider, now, this part's not hard, kx equals 20. The thing here is what x is about. X is not about the length of the spring. And if I led you to believe that yesterday, I was wrong. X is about the change in length of the spring. And your book puts a delta here. I don't put the delta there because traditionally it's not listed as a delta because there are other types of things that change. So you would put 0.05 there to indicate the spring changed by 5 centimeters. And therefore K is equal to 400 newtons per meter. Do I have to do part 2 of this where we just replace this now with a 3 kilogram mass? I ask questions like this not to insult you, but just to make sure if you do need me to do the other part, I will. I don't know if you need me to do that. Now that you've seen this, is that enough? I don't care. So we're good? Okay. If I was giving this problem as a quiz today, subtext coming through, I would maybe ask question A, but my version of question B would be a little different. Where question B just puts a heavier weight on there, my version of question B would be different. I would say, okay, now that you know that the Hooke's law constant is 400 newtons per meter, you pull the weight back up so that it's right here, and you let it go. What is the maximum displacement of the spring? I was told in third period that students have difficulty with the, let me just kind of redraw this a little bit so we have some points to work from. I don't need the equilibrium position anymore, I just need that starting spot. So it starts here, I release it from here, and it goes till it's here, where the velocity is also zero, and velocity is zero here. And then after this point, it goes back up. Now, there are a lot of stupid things here that I think I can use for problems. One of the things is an understanding that we had to pass through the equilibrium position. The equilibrium position was like here in the middle, right? It was at equilibrium where the net force was zero. So when I was on this side of equilibrium, the net force is downwards. The spring is not stretched very much, and the weight is greater than the spring force. So it's accelerating downwards. Here, when I'm on this side, the net force is upwards. The string is stretched further than equilibrium. It's pulling up more than the weight is pulling down. So it spent all the time going to the equilibrium point speeding up. When it got here, it was at equilibrium, net force was zero, but it was still moving. And it couldn't be stopped here because it needs an acceleration upwards to stop. So when it passed that point, every place after that, the acceleration was upward, slowing it to a stop, which is why it stretches the spring out. That's inertia. It takes an unbalanced force to get something to stop. So your job, or our job, is to figure out how far down it stretches out the spring. And as I said, the total work is zero, because the total change in kinetic energy is zero. Kinetic energy never asks you where the object is, so the fact that it moved isn't really featured here. It's just that the change in kinetic energy from the top to the bottom is zero. Let's pick a point in the middle. Name the forces acting on the object in the middle. Go ahead. Yep, so I have weight downwards. Weight's a constant. That one's going to be easy to deal with. So when talking about the work done by gravity, that's be pretty easy to deal with. It's going to be a force times a displacement times the cosine of the angle. We're going to need to give this displacement a name. So is just D okay with you guys? Would you rather be X? I don't care. D okay? So the work done by gravity will be 20 newtons times the unknown length that the spring is stretched times the cosine of 0 degrees. The weight's downwards, the displacement is downwards. Good so far? What's the other force acting on the object? Spring, right? The tension. What direction does it act? Got to be upwards. It acts on the spring the whole time too. It acts on the mass the whole time as well. The problem is that I can't use this to figure out that work. The force from the spring was constantly changing. So I have a choice. Integrate or use an expression for the work done by a spring. We developed an expression for the work done by a spring, so that's what I'm going to do. But you're welcome to integrate if that makes you feel better about yourself. But there's no reason for it. It wastes too much time on the actual test. So I'm just going to put 1/2 kd squared in place of force times distance times cosine. But that doesn't stop me from having to deal with whether this particular amount of work added to the kinetic energy or took away kinetic energy. Did this one increase the kinetic energy of the system or decrease the kinetic energy? It's decrease. Look, you can still ask yourself the simple question. It's going downwards, but the force is upwards. That's got to be a cosine of 180 degrees. So this is negative. It is taking kinetic energy away. Now, on the way up, it's doing the opposite, but on the way down, that's what it's doing. This has to add up to be equal to 0. Now, there are other ways to do this question. We're going to learn about conservation of energy after the break, and it's the same problem, just slightly different in the way we formulate stuff. But at this point, I think this is not too hard to do. Just going to add these up, set it equal to 0. So I have 20d minus 1/2 times 400 d squared equals 0. D represents how far the spring was stretched, which is not actually true, because we're going to get 2 answers, right? 2 answers. If I factor out and divide by 20, this is d minus 10d squared equals 0. Right? Half of 400 is 200. 200 divided by 20 is 10. So now I have 2 answers. I can factor out 1d, set it equal to 0. And then I can solve for the other d and find that it's 0.1 meters. The reason there's 2 answers is not obvious, maybe. I asked the math to tell me where the object has no kinetic energy, and it told me. It told me when I first started, there was no kinetic energy. And when it made it 10 centimeters away from where it started, there was no kinetic energy. Okay. This also proves that it oscillates back and forth an equal distance from equilibrium, which was at 15 centimeters, 5 centimeters from here. That's where equilibrium was. So it went equal distance this way and this way when it was bouncing. I like that question. That could have been a quiz question. You might not like it, but it's not terrible, is it? It's not terrible when I do it. All right. Is there anything else on the homework that's not a power question? Because what I'd like to talk about now is power. Yes, sir. 51. All right, that was this is 51. We are told that we have a real spring, which has a force that is more complicated than the ideal spring. This is the force that we get from our real spring. This is not a real spring. They're just trying to give you a function that you can use for a question like this. Real springs are different than this, but it's okay. It's fun. It's an easy question. I'm going to go ahead and put in the 250 and the 800. That way our function is a little simpler. We are going to do work on this spring. We can't use our standard definition of work for a constant force because the force is changing in a complex manner. Would you agree? We'll have to use our expression for force that allows for a change in the size of the force over the course of the displacement. What that means is, to find the work done, I will have to integrate this equation. Now, I understand, for all of you who don't have calculus, this is all new. But the first thing I have to do is substitute in my function for force. And the function I substitute in has to have a variable that represents displacement, or else it doesn't work. Now, moreover, when you guys are taking notes here, it doesn't have to be x. This x here is a placeholder that means displacement. So whatever your problem is using for displacement, I mean, the problem that we had s there. Delta s, no less. That still just meant the displacement of the spring. I'm just going to use x. But I could just as easily say, for s, I would just have to make sure I understood that this 2 would have to be s. because it's supposed to be whatever the displacement variable is. Does everybody understand? If not, write it down so that you at least have it to talk to yourself later. I can leave it in terms of S since that's what the problem is in. But I also want to say that we're not done setting up our integral. We have to tell our integral where the spring begins and where it ends. We start without any compression of the spring, and we end when the spring has been compressed 0.15 meters. These are the limits of integration. Now, our job is twofold. We have to execute the integral, and we haven't done this very much, but it's 2 steps. Step 1, find the antiderivative of the function. That's step 1. Now, it's going to take time for you guys to appreciate some of these things, but this is the function. It's bracketed by the integral symbol and the ds or d whatever. This thing is telling us what is the important variable and everything else are constants. This is just giving us a place to hang our limits, but it acts like parentheses. You can factor things out, stuff like that. It works the same way as parentheses. The only thing that can't be factored out is anything that has that variable in it. So I can't factor the s out or anything like that. All right, next step, or first step, antiderivative. This is a polynomial. If you don't remember the antiderivative of a polynomial, like x to the 1, the antiderivative is you add 1 to the exponent and you divide by the new exponent. That's the antiderivative of a polynomial. So that's what I must do here. I'm going to add 1 to the exponent and then divide by the new exponent. So take my exponent down, s, add 1 to its exponent. The exponent's not listed, so that means it's 1. So add 1 to that and get 2, and then divide by the new exponent. So divided by 2. Don't forget there was a 250 in front of it. It's a polynomial. We've done it for the first nomial. Let's do it for the next nomial. Minus s, add 1 to 3 and get 4. Divide by the new exponent, which is 4. And don't forget the number that was in front of it. Move on to the next nomial. Oh, there isn't one. We're done. This is 2 nomials in our polynomial. All right, that's it. We have done the antiderivative. That's step 1. Step 2, apply your limits. Once we've done with this, we can get rid of the integral symbol, but we are still responsible for actually conducting the integral, which means to apply the limits. Applying the limits isn't hard. It's just a step that we can't forget. And what it means is to substitute this in for our variable, and then substitute this in for our variable and subtract. That's the first one. I put into 0.15. I don't have much room here, but is it okay if I just put minus 0 since the next thing I'm going to put in is 0 and it zeroes out everything? So that's what you had to do for this. This is the amount of work in compressing it. Now, the next thing they ask is for you to find the amount to compare this to the work done on an ideal spring. That would just be comparing it to what it would be if it was 1/2 k x squared. You're making that comparison, leaving out this term and finding out how much work was just here. And you're going to find that there's more work with the real spring because you have this term too. So that's all they're looking for in this question. And I need to move a little forward. So if you didn't get this on the first pass, that's okay. I want you to hear this clearly. I'm going to have calculus examples in every homework from now on. I'm expecting you guys in calculus to be doing these. You guys have had physics 1 already to be doing these. I'm expecting you guys who are in pre-calc to be asking about these. Does that make sense? I will ensure that we go over the ones that have calculus in them every time. but I will not be testing calculus until second semester, and it's not on your semester exam. The only thing that might be on your semester exam is what we did at the very beginning of the year with motion equations. All right. I am of limited time, so I need to just put something in front of you, and I'm just going to put the definition in front of you. I don't expect you to spend much of your break sweating this, so don't. Power is the rate it's the rate at which work is done. It's the rate that you consume energy. So far, everything we have done about work has never once mentioned time. Power is the answer to that. Power brings in the concept of how fast the work was done. That's what rate means. Rate can translate into fast. How fast was the work done? How fast did you consume energy? So when we talk about a rate, it tells us how fast something is happening. There's three different ways I can write power. There's the algebra way, which is work over time, or energy over time. But we're talking about the consumption or change in energy, not just how much energy you have. So this should be like a delta energy. The units are going to be joules per second. It's energy over time, joule per second, which is kilograms meter squared per second cubed. It's a mess. But it has been named the watt after Mr. or Mrs. Watt. I don't know. 100-watt light bulb consumes 100 joules of energy every second. That's what it means when you say something's wattage. If you have a 1,000-watt microwave, 1,000 joules of energy every second. That's what that wattage means. So it applies to electricity. It applies to physical work. Generally, it's how fast you do work. So if you're lifting a piano, this would tell us how fast you get the piano up to the second floor. But if I just want to know how much work is done, you can take all day. A more powerful motor does work faster. So a moped and a Mustang can both probably get to 40 miles an hour. Which one's going to get there faster? I don't think there's even a question. One of them is more powerful. It will do the work faster. The moped will not get up to 40 miles an hour very fast, in case you were concerned. Now, we're going to have our quiz, but you need to see this. Work is force times distance, right? Divided by time means power could be written as force times velocity. In a situation where there is a constant force, the rate at which power is delivered, which is the way they write it in the question, is force times velocity. So all those questions that ask about power, almost every one of them is this. That's why they tell you how fast the object's going. They say it's going at a constant velocity, so no work is being done, but the engine still supplies power. This is what they're talking about. All right, you must take your quiz now. So sorry. You need a pen or a pencil. Go ahead and get your red pens out and your highlighters. We will have adequate and sufficient time. You may pack away your other belongings, or you will not have to do anything else. This is a timed test, so please. Oh, and it's multiple choice. I know, to be mean. There are 7 multiple choice questions. So please do not turn it over until you've been told to do so, because I think you guys are going to be cheaters. And I want to make sure I watch you carefully to ensure that there is no cheating, no sharing of answers. Well, Mark, be sure I can see your first class. get set, go. You may write directly on it. It's a quiz, no talking. There are right answers, by the way. If I put a marble at the bottom of a bowl, it will stay at the bottom of the bowl. Would you agree? If I displace the marble to the side, immediately there is a force that is created by the normal force and the weight that will push the marble back towards the center. Would you agree? That would be similar to what a spring does. You push it to the right, the spring pushes back to the left. If you have a plus here and not a minus, if you push something to the right, it goes to the right and the force increases. Now, if you can't imagine that, just turn the bowl over. I have an equilibrium position. I can put it right precariously at the top. But in this case, if I displace it, will it go back to the center? No, in this case, a force is created the moment it's displaced that will attempt to push the object further away from its equilibrium position. So the negative sign has physical meaning. It restores our system towards equilibrium. The positive sign would be destructive. We want to build buildings that do this. We don't want to build buildings that do that. Right? We want, if our building gets displaced to the right because it's an earthquake, we want there to become forces that will push the building back to the left. We don't want, when our building is displaced to the right, there become forces that push the building off its foundation. And I know it sounds silly, but this is why you study this. You don't study it because the spring is important. You study it because one day you might be designing a building. And if you are designing a building, understanding structural stability starts with understanding restoring forces. So I hope that in the grander scheme of things, you understand that what we study here is not always about you having to have a foundation on how springs work. There's more to it than that.